In this very first episode of Space or Bust, you're going to figure out why a geologist wants to build a rocket. And yeah, you did hear that right in the introduction. My name is Matt, and I'm a geologist, and if you don't believe me, I have the hammer to prove it. Old reliable. And you might ask yourself, what the hell is a geologist doing building rockets? And to answer that question, I have to take you back to the very first days of college. When I started out as a wide-eyed freshman, I really had two choices. Option A was to be an engineer. Go do math, go build rockets, so on and so forth. Turns out that I suck at calculus, which is something I learned the hard way. So that was kind of off the table, but I still love space, and it's always been something I've cared deeply about. And then I discovered option B, which, as it turned out, was planetary science. So I went down that path and became a geologist. But I never really gave up on my dreams of being involved in rocketry or the space industry or really anything space-related. So I went out and I found the high-power rocketry team on my campus, and I joined it, which made me the only non-engineer on that entire team. To get to the point of this video, or why this series exists, you have to understand a little bit about a few things. First of all, I want to assail your fears that I don't know what I'm doing, because I vaguely do. At the very least, I know how to do fine dining and breathing, but we'll get into that. The main reason I want to do this is I want to run through some of the basics and show you why I totally think this is possible, and go through some of the logic that led me down this path almost a year ago when we were designing the space shot. So, let me walk you through some of the fundamentals real fast. You've probably built a little Estes kit before, and I have one over here that I can show you just for illustrative purposes. You know, it comes in a box like this. It's got a cool rocket on it. It's got all these little warnings. It's got the motor classifications here, skill levels. You get the idea. And when you pull it out of the box, you get this little bag. You know, you got your body tube. You got in here, you got your fins. You know, it's a really straightforward process, and I'm sure that if you're watching this, you've probably built at least one of these in your life. And you know what they run on, which is, if you're doing the right thing and buying motors instead of trying to make your own, we'll talk about that in another episode. You see these little motors. Aren't they cute? Cute little Estes motors. These are basically the baby junior version of the kind of things that the high-power rocketry community plays with. I mean, they're a little different because they use a different propellant, but they are more or less run off the same principles. There is a solid fuel in here that burns or regresses when the motor is ignited, and it provides thrust. Really nice, short, sweet, and simple. So, of course, there's kind of an adult-y version of this, in which if you're over the age of 18, you can legally go out and build your own rockets of pretty much whatever size you want up to a certain point. There are some certification levels, which we'll talk about in a little bit, but they all run off of more or less the exact same principle. Except the bigger motors don't quite burn like this. These are what's called end burners, in which case there is the propellant on the inside and it regresses steadily backward until it burns out. You can see the little nozzles on the inside there if you look closely. High-power rocketry grains actually look something like this. We all know what this is. And the way they work is more or less by the same principle, except instead of having propellant burn downward from a flat surface, it actually burns in this core, or the bore of the propellant, which is represented by the toilet paper roll on the inside here. It regresses backwards from this to the edge, and that's when it burns out. And this means that you can get a lot of power and a lot of thrust out of one of these things versus an end burner, because if you can imagine an end burning grain would just have this flat surface on the top and it would walk backwards, versus this tube has a lot of surface area. In fact, I'm pretty sure that the surface area of the tube in here is bigger than the total surface area of the grain. So you can get a lot of thrust out of these, and that means you can make really powerful, really big motors. And this means, of course, that you can go really far. Let me explain why I think this is completely possible, or at least walk you through the chain of logic that led me to the design that I have for this space shot. Getting to space really isn't that difficult. By most legal definitions, it's about 100 kilometers above your head, which means if you don't live within about an hour of the seashore, you are closer to space than you are the ocean. And all you're really doing is going up, going past it very slightly, and coming back down. That's the definition of a space shot. So all that you really need to understand here is that for the most basic and simple version of any of this, it's literally just the relationship between your gravitational potential energy, which is mass times gravity times height, if you remember from physics class, and that initial burst of kinetic energy, which is 1/2 mass velocity squared. If you want to know the exact velocity that you need to reach to get to the edge of space, it's actually really simple. You take these two equations and you set them equal to each other, or 1/2 mass velocity squared is equal to mass gravity height. You'll notice very conveniently, of course, that there's mass on both sides, so you can ignore it. And the very simple equation for getting a rocket to the edge of space is literally just 1/2 velocity squared is equal to gravity times height. And that velocity usually comes out to be about 900 meters per second, which is a lot in human terms, but in spaceflight terms, it's almost nothing. The big rockets like the Falcon 9 or SLS or anything like that, or the Saturn V, for example, they had to get to orbit, which is a lot more sideways. And I won't go into the particulars of that because that's definitely a subject for a whole lecture series, but they need a velocity of about 9,000 meters per second. So it is totally possible to get something very small to space. The velocity is actually relatively low. This is about Mach 4 or Mach 5. Which, of course, gets me into the main considerations here. To explain a little further about the particulars of this, now that we've gone over some of the basic math, we have to understand the atmosphere. It's very thick down here at the surface. It's very thin at space. It looks something like this. So there's a big, thick atmosphere here that you have to cross through if you want to get to space. And that means that aerodynamics becomes a very important consideration in all of this. Our little rocket has to go through this big, thick layer of air before it can get up to the area where it'll behave more ballistically. This place will have to deal with drag. And the equation for drag is just 1/2 CD. This is a dimensionless value called the coefficient of drag. It's measured experimentally, and it tells you basically how much drag per unit area that your object produces, times the cross-sectional reference area, times the density of the air, or rho, which is what we're dealing with right now, and that's times velocity squared. Wow, I didn't write that right. But this is your drag equation, and it means you really, really want to lower this value, because rho you don't really have that much control over, because it's the atmosphere. If you can change the density of the atmosphere, we have very big problems on our hands. But coefficient of drag times the area is really the best thing that you can contend with. And what that really boils down to, and to make a long story short, is you want a very long and thin rocket, because you're exchanging some of that cross-sectional drag, that reference area drag, for body drag, which, if you've done it right and you have a very polished surface, is predominantly laminar. In other words, air flows past it very nicely, so this is very low drag. Thing is rockets don't like being long and thin. I'll pull out the toilet paper tube model again to show you. This doesn't like being thin. In fact, because that thickness of that grain determines your burn time, you don't really want that to be long and thin. It'll be a very short burn time, and the surface area on the inside will be very high, and that determines the thrust, as we discussed. So with a lot of thrust and very short burn time, it means that you're in a position where you can have combustion instabilities, the grain spontaneously falling apart, lots of nasty things. Rockets don't like being long and thin, but drag wants them to be long and thin. And what this generally means is that most really big rockets, like the kind that space shots have been, they don't really tend to be very small, even though the potential for making them small is there. And USCRPL's Traveler 4 was something like 2,500 pounds in total, which is a lot. So you might think to yourself, well, building a rocket that's 2,500 pounds, that's ridiculous. That's an incredibly big rocket. But you don't really need to. Because in the 1960s, there was a group of engineers that developed something called the Super Loki sounding rocket. And they kind of had a realization. Make the rocket part be a rocket. And then put all of the instruments in something really long and thin, or a dart. And this was the genesis of the boosted dart concept. Your motor, in other words, doesn't act as your main propulsive force throughout the entire flight, resisting drag, whatever. It throws a very small and thin instrumented dart really, really hard and fast, which optimizes for this value, while the booster is optimized for the actual throwing of that dart. And this means you can actually have a really tiny rocket. Somewhere on screen I'll try and post a picture of it, but the Super Loki sounding rocket was only 68 pounds. Which is a lot smaller than Traveler 4. So, of course, this consideration behind this means that you need to basically make your own custom motor, long story short. That's not impossible, but it's a lot of pain to do. Making high-performance motor grains yourself is probably one of the scariest engineering things you can possibly do. And I know this because I've worked with the propulsion team in my university. It's really hard to get right. like, I'm sure you've probably seen those videos of people on YouTube making little sugar motors out of PVC, and that's very dangerous. And to reiterate, like, some of the danger here that I've been told secondhand, there's a couple things. Well, first of all, even though I throw around these little Estes motors somewhat lackadaisically, there's a lot of energy in here. I can take you back to that initial drawing that I did. If you're going up to that altitude, you can understand that the chemical potential energy has to be a function of this kinetic energy. Maybe it's a 50% loss, 90% loss. I'm not entirely sure what the specifics would be. But one of these little tiny motors can actually carry a lot of energy. I think one of the estimates I've seen is that a high power motor like this, or a low power motor like this, can carry about as much potential energy in it as a hand grenade, which is a lot. These are meant to be respected. Making your own is very challenging, and something that I would only even dream of attempting if I had, like, years of time and experience behind it. But that's not to say that getting to space is impossible under this idea, under this strategy, because the biggest motors available right now are actually just barely capable of doing a boosted dart to the edge of space. And that's where I will introduce my plan. So this is the plan. This is the space shot vehicle that I've conceived of after a lot of effort and research. This is what I've settled on. The first stage, you'll notice, is called an O5280 booster. And that probably doesn't mean much if you're a first-time Rocketeer, but it actually ties into the system of classifying rocket motors, as I briefly touched upon. You'll notice that these actually have a little letter in front of them, C6-5. And you might wonder what that means. The 5 is the delay, how long it takes for this to burn and then fire the ejection charge, but that C6 actually represents the thrust class of the motor. Every motor is classified based on impulse, and if you remember from physics class, all impulse is force times time. In this case, it's the average thrust times the total burn time of the motor. So these little C6-5s are determined based on a table of impulse classes, and I'll throw up a little picture of that on the screen. You might think, of course, that a C and O aren't separated that far, but that's far from the case. Each letter up represents a doubling of the impulse. So a D motor would have twice the impulse as the C. This O motor has about 8,000 times as much impulse as a C. It's very big. And how big, to put it in perspective, this is effectively the largest commercially available rocket motor that we have right now. That big motor goes into a little tiny sustainer. It's an L2050, which is a little bit smaller, as you can kind of imagine, but it's also smaller in terms of diameter and size. This motor is actually about 4 inches in diameter, or 98 millimeters. We use the terms interchangeably in high-power rocketry. And I have a little coupler tube to just show you how big that is. The motor, of course, would be about 5 feet long, and this is about a 9-inch piece of 4-inch tubing that I have from the Space Shot project. But you can kind of imagine how big this thing is going to be, just to drive that point home. This is probably some of the largest motors that you might have ever flown if you've done amateur rocketry. So that goes to an L2050 sustainer, which is about 2.5 inches in diameter. I can hold up my hands to show you. About that big. And the trick here is marrying the idea of a boosted dart with a two-stage vehicle. I think what the key innovation is. This sustainer, much like the Super Loki sounding rocket, has a tail cone on it. When that motor fires, it separates the tail cone, but until that motor fires, it's actually very aerodynamic. Aerodynamics does not like having a flat surface on the back of objects. If you've ever seen the back end of a Prius, you know how it's got that kind of funky, curvy shape to it? That's to help reduce drag. This tail cone reduces a tremendous amount of drag and basically helps make this possible. By having a very highly aerodynamically efficient sustainer and a very high thrust booster, a space shot is possible. This particular design I've simulated a few times, and I've gotten to about 350,000 feet. Edge of space is about 328,000, so there's a little bit of wiggle room in there to actually make this happen. Of course, like everything, there are a couple caveats. The biggest one, first and foremost, is the fact that I touched upon this very briefly. You can't just go to your corner store and buy an O5280. They're very big. They're very expensive. You need certifications. In fact, there are 3 levels of certifications based on the amount of based on impulse. regular people can go out and buy these because they have a low enough impulse that you don't need a license for them. They're relatively low energy, and in the eyes of the government, they're mostly harmless. But beyond that, you need to tie into the two regulatory bodies of high-power rocketry. First one is NAR, the National Association of Rocketry, and the second one is Tripoli, or TRA, Tripoli Rocketry Association. And you'll actually notice that these motors are certified by NAR. You can kind of see a little picture there, and if it doesn't come out well in video, I'll post an overlay. But they are the two governing bodies, and you need to abide by whatever regulations they have. Which brings me to the subject of this series. Because of a number of clerical errors, I actually never got my certifications when I was part of the high-power rocketry community, the high-power rocketry team. So I need to go on the journey of starting literally from scratch to make this space shot happen. And the way things are going, I think I'll have all the parts in place to accomplish every single level of certification by hopefully the end of the summer, but we shall see. But I'd really love to take everyone along on this journey, because there are a lot of people out there that are getting excited about space and rockets and technology, and I just don't think there are enough resources available right now. Everybody defaults to the videos of that one guy that made those deadly sugar motors and doesn't really move beyond that, and I think that the hobby can be a little daunting at times because of how confusing it can be. But having someone go through the motions of literally from this level of technology to getting something to the edge of space is, I think, a really compelling story. Which brings me to the subject of space or bust. I'm building this rocket to get to the edge of space, and I want to take you, the internet, along for the ride. So that's where we're at. I have a few parts on back order for my first certification that I'm going to be attempting in the next few weeks or months, and I will be taking you with me along the way. Until then, this is Matt from Space or Bust, and I hope you all fly safe.